Pick up your valve amplifier and you might notice that all of the weight is on one side of it, making it a pain in the shoulder to carry. But before you take up arms with the amplifier companies, just know there's a sound reason why they've designed them this way. I'm going to take a look inside this Orange Custom Shop 50, a prime example of hand-wired opulence to help you understand amplifier design and hopefully separate marketing myth from reality. Before we go any further, here's your obligatory safety warning. Poking around inside a valve amplifier is potentially dangerous. In operation, there are high voltages of both the AC and DC variety pushing lethal current around this amplifier, and there are components in here that will store that lethal charge for some time after disconnecting the amp from the main supply. Touching the wrong thing inside this amplifier could lead to serious injury or death. So please do not emulate anything you see me do in this video if you aren't already comfortable working with live electricity and know how to safely discharge capacitors. I do not wish to be responsible for an amplifier not only killing you, but it hurting the whole time it's happening. This is how it looks to be on the inside of a hand-wired amplifier. The first question you might have is, what do all the bits do? Well, instead of me spending the next 10 minutes pointing at everything and explaining all of that, you'll find an addendum video linked in the description and the pinned comment which will give you all of that information. What's the deal with all of the weight being on one side of a valve amplifier? Well, this is the culprit right here. This big beefy bake is the mains transformer, and it contributes significantly to the overall weight of the amplifier. And you'll notice it sits all the way on the far side of the amplifier with nothing big and heavy on the other side to balance it out. Its job is to take the mains electricity from your wall socket, 230 volts AC 50 Hz here in the UK, and it transforms that into all the different voltages required by the amplifier. From the small 6.5 volt AC for the preamp valve heaters, up to the 400 plus DC supply for the plates of the output valves. The wires that distribute power to and from the mains transformer carry significantly more current than the signal wires. That larger current flowing through the mains wiring and the mains transformer itself radiates electric fields around themselves, and should those electric fields come into contact with a signal wire, they will inject interference and noise into the signal, which will inevitably get amplified. We obviously don't want that to happen, which is why we see this interesting twisted wire pattern throughout the amplifier. Power wires come in pairs, a live and a neutral, a positive and a negative, a send path and a return path with current flowing in opposite directions in each. With opposing currents, we also have opposing electric fields, and if we can get those fields to combine, they will eliminate each other. By twisting these pairs of wires tightly together, we can eliminate the majority of the opposing electric fields that radiate from the wires, significantly reducing the potential for noise in the signal being amplified. If you are wondering how amp builders manage to get such neat twisted wire pairs, then all you need are your two wires, chucked up into a drill and secured at the other end. It really is as easy as that. We can further protect the signal path from stray electric fields by running all of those twisted pairs into the farthest corners of the chassis. The entire chassis is implemented as a ground plane, capable of carrying away any electric fields that come into contact with it, which helps to shield the signal wires from outside EMI, as well as remove any residual fields spilling off these internal power wires. By keeping all of the power distribution components contained to one side of the amplifier, farthest away from the wires carrying the weakest signals, and ensuring that the wires that do carry power throughout the amplifier are twisted together and tucked into the corners of the chassis, we ensure the quietest possible operation with the least chance of noise and interference from the power supply. Speaking of features that help reduce noise, take a look at this little cutie. Beautifully executed in this amplifier is a star grounding point, where all the different ground connections from different points in the amplifier circuit are collected together to one single point on the chassis. Now, why would you bother doing this? The whole chassis is a ground plane. We could terminate these anywhere we like and still have a functioning circuit. Why drag all of these long wires across the amp to make a pretty little star like this? While we like to think of all the grounds as being at a consistent, stable 0 volts everywhere, that's far from reality in devices like this. Ground connections at different points in the circuit may be setting at slightly different voltages at different times, and if we connect all of these points to different places on a sheet of conductive material, those differences in potential are going to start pushing currents in loops around the chassis. If we've got currents, then we've got electric fields, and oh no, we've just injected ground hum into our signal, which we obviously don't want. By ensuring all the ground paths meet at a single point on the ground plane, we eliminate the possibility of ground loops circling the chassis and keep the amplifier quieter as a result. Now, some of you might be going,
Well, actually, Colin, star grounding can introduce its own set of problems.
Yeah, let's address those real quick. Dragging long ground wires across the circuit to reach a common point on the chassis does run the risk of those long wires acting as antennas that pick up EMI, but that's far less of an issue here than the ground loops would be. So we place the ground point as central as possible to minimise those cable runs. Star grounding also tends to be detrimental if you're dealing with high frequency signals, anything in the megahertz region or above. Fortunately for us, audio frequencies clock out at 20 kilohertz at the highest, a whole 2 orders of magnitude below where star grounding would present an issue for signal amplification. So for our applications, guitarists, star grounding has more benefits than detriments, which is why it's such a common approach in the construction of hand-wired amplifiers. Point-to-point describes the construction methods of electronic circuits that predate, or in this case, emulate circuit styles that predated printed circuit boards, where components would be soldered directly to each other without the use of wires or traces to make the connection, often supported mechanically by tagboard or turrets. If one component connects directly to the next, and to the next, and to the next, then that's point-to-point, to point-to-point. This amplifier uses turret boards to support the point-to-point construction in the main circuit and the rectifier. Now, if you're one of those insufferables that says things like,
Well, it's not true point-to-point because it uses turrets,
then that's the kind of worthless pedantry that is preventing you getting laid. The turrets aren't magically preventing the circuit components directly connecting one to the next, and they also provide convenient attachment points for any wires that are required to connect components like the preamp valves or the front panel potentiometers, which have to be in different locations for reasons of blatant obviousness. If you listen to the forum dwellers who've been taken in by the marketing, you might hear claim that point-to-point construction offers a purer tone because there's nothing between the components to interrupt your sound. Personally, I don't think that's the advantage that point-to-point offers. A properly designed PCB layout isn't going to sound any different to the same circuit designed for turret board, and point-to-point has its own disadvantages. It's an archaic construction method which is unscalable and unable to be automated. It takes up a larger footprint than the equivalent PCB layout, and it's more expensive and time-consuming to implement. The main advantage of point-to-point turret board construction is that it's very pretty to look at. And for small-run, handmade audio devices, the larger components and the easy-to-visualize layout aids in both assembly and serviceability. When I made my fuzz face, I chose turret board point-to-point for those very reasons. It looks great, it was very easy to demonstrate in a YouTube video, and if anything goes wrong, I can easily identify and fix the problem. And since I was only making one of them, it made sense to indulge in a little bit of traditional circuit design. So if you see point-to-point being highlighted in the marketing of an amplifier, don't be tricked into thinking it'll somehow sound purer or whatever. It's just letting you know that this amplifier is constructed using traditional handmade methods. If that's something you value and want to pay more for, then definitely look for point-to-point. Class A is a proudly boasted feature of pretty much any audiophile amplifier equipment, because its linearity sounds so much more natural and you can get the true warmth of analog valve saturation. But what does any of that actually mean? The difference between Class A and Class AB amplification is a technical distinction that boils down to how you bias the power valves. We can consider bias as the idle current of the valve. How hard is the valve working while it's not under load? If we have one valve with a high idle current, that gives us the capacity to amplify the whole waveform at once, which is great for linearity, but because of the high energy cost, we sacrifice total power. The waveform will hit saturation pretty quickly. A single EL34 power valve typically has a maximum output of up to 30 watts in this configuration. This would be Class A operation, and with only one valve, we'd call this single-ended. But there's nothing stopping us adding a second valve to amplify the phase-flipped copy and have this operating in push-pull. Even though both valves are conducting across the entire signal in Class A, each will conduct harder in their respective hemicycle. This sharing of work between the valves is seen even more clearly when we lower the idle current. Now, each valve is only capable of amplifying maybe 70% of the total waveform, but because we have a pair of valves working in push-pull, the second valve is able to make up for the losses of the first valve, and vice versa. When recombined, this gives us a complete waveform with minimal disruption to its linearity, and because each valve was only handling a bit over half a waveform each, it increases the total power output, giving us significantly more headroom. This is called Class AB, and the two EL34 valves in this arrangement can reach a maximum nominal power output of 50 watts. The class selection switch on the back of the Orange Custom Shop 50 is engaging with the biasing components on the turret board, bypassing the components that would lower the idle current, letting us recalibrate the output valves from 50 watt Class AB to 30 watt Class A for more linearity, less headroom, and a different feel to the interaction of the amplifier. In short, Class AB has more headroom, will feel tighter in response, and will probably be the experience you'd expect from a valve amplifier. Class A will saturate sooner at higher volume, will feel looser in the low end probably, and make you feel like an audiophile if you can perceive any of those differences. One is not superior to the other, they are just two different methods of achieving power amplification with slightly different responses under high volume applications. It's a feel preference thing more than anything else, and is most noticeable when you are the one operating the amplifier. I personally prefer this in its Class A 30 watt mode, but I think that's because it brings the feel and sound much closer to what I'm used to with the Orange AD30. Another gimmick of this amplifier is the foot-switchable EQ lift, which I personally think is genius. It's a very clever way of giving a simple single-channel amplifier the equivalent of a second channel or a boost mode for free. The way it works is that the EQ stages in amplifiers like this are entirely passive and subtractive. They don't add any extra frequencies to the amp, they just take them away. The raw amplifier is voiced to be louder, gainier, and more frequency rich than it needs to be, and the three EQ controls and the passive filtering components they are connected to work to remove the bits of the sound that we don't want, sculpting down from the wild, untamed amplification into something more refined for our use. Even with the controls rolled up to 10, we don't get the full force of the raw amplifier. Simply having these components in the circuit loads down the signal and reduces the volume, gain, and frequency content. This foot switch control allows the entire EQ section of the amplifier to be disconnected from the circuit, giving us the true, unaltered aggression of the valve amplifier. Thicker, hairier, louder, better? Well, I'll let you be the judge. I don't want to misrepresent hand-wired amps as being the apex of effort and skill, and diminish the mastery of good PCB design in the process. To design an effective low-noise circuit with either of these methods requires very different but equivalent knowledge and expertise. However, it is much easier to look at the hand-wired amplifier and see the effort displayed visually in the assembly of the circuit. Even if you know nothing about electronics, when you look at this, it's obvious to see where the effort went in the construction and find it impressive. Whereas PCB looks like a PCB, no different to the hundreds of identical boards that were machine assembled and rolled off production line the same day. That tends to have people interpret PCB amps as lower effort or less skillful than their hand-wired counterparts, but that's not true. The hours of human effort spent on PCB is in the design phase, where engineers sit in front of PCB design software, agonising over trace widths, clearance, via diameters, ground fills, and many other factors that need to be considered to ensure issues don't arise with signals and powers travelling through the copper traces. We talked about how, with hand-wired design, power wires need to be routed away from signal wires to prevent the electric fields interfering with the weak signals. And that same physics is true for PCBs. Power traces need to be wider to carry the required current, but they can't be placed parallel to signal traces for the same reasons of electric field interference. It's just easier to see in a hand-wired amp the twisted pairs of power wires being routed around the chassis perimeter than it is to identify differences between green traces on a green board. And with everything being packed much more closely on a PCB, these design challenges become much trickier. PCB does have its physical limitations, but so does hand-wired, and so long as each is designed or constructed properly by people who know what the fuck they're doing, there shouldn't be any vast observable difference in their sound. I'm pretty confident in saying that if you took this circuit and redesigned it to work on a PCB, you could play these side by side and not be able to tell one from the other. Especially once the guitar has gone through your instrument cables, maybe a couple of pedals, the amp, out to a speaker, into a microphone and back through a PA system. At that stage, are we really noticing the difference between electricity going through point-to-point component legs compared to a copper trace? I'm not saying these two things behave necessarily identically on a subatomic level, but given the whole context of the system, any variances are so small as to be negligible. There may not be any sonic advantage to choosing hand-wired over PCB construction on a purely macroscopic level, but there is on a psychological one. You are investing in a work of art, and knowing that your amp looks pretty on the inside might change how you approach your performance. If it makes you more confident and results in you playing a different way, then it will absolutely make you sound better. And at the end of the day, that's all that really matters. If this makes you feel good and makes you play better, then this is the amplifier for you. Hand-wired valve amps are what excites me to pick up and play. I mean, I'm bricked up just looking at the guts of this amp. It's the traditional technology that's part of the enjoyability for me, while something like a digital processor floorboard never gets me beyond flaccid, regardless of how good it sounds. But if none of this makes a difference to you personally, save your money and buy something else. I promise you're not missing out on some super special secret tone by not buying a hand-wired amplifier. If you are looking for practicality and affordability in whatever configuration you can get it, hand-wired should be the last thing you look at. As always, purchase links to the amp and the guitars used in this video can be found in the description and pinned comment. Hopefully this has helped you understand hand-wired amps a little bit better, and if you do have any further questions, please do leave them in the comments. That's all for now. Keep it loud and stay safe.